Hello students and welcome to this session. My name is Anoop Vashishtha. I am an MSc in Chemistry from University of Delhi and you are on Unacademy NEET Elixir channel. Am I audible and am I visible to all of you? Yes. So, what do you want to say, Sarthak, Prerna? Good evening, beta. Good evening, Ananya. Good evening, Radhika. Good evening, everybody. So, are you able to hear me? Now, again, today's session is going to be an extremely important one. Of course, we are going to take only the important session. We are not going to take certain unimportant sessions. Today's session is going to be about the osmotic pressure and we are going to talk about abnormal molar masses. Now, abnormal molar masses, that is the Vanta factor that we are going to discuss and we are going to see why the abnormal molar masses are there. So, let's begin over with it. So that's about me. My name is Anoop Vashishtha. I am an MSc in Chemistry, 26 years of teaching experience, lakhs of students and teachers. And now I am with you on this particular channel to teach you the part of chemistry. Okay? And you need to remember today at 5:30 p.m. we have a special class. This special class is going to be having the questions from the concentration units. These are extremely important questions and you make a lot of mistake when we talk about the concentration units. So, we are going to talk today about the concentration units. Okay. Good evening, beta. And at 7 p.m. we have a special session and we are going to introduce a new educator to you. So, 7 p.m. remember that. We are going to be live on this channel. So, your entire schedule is already made. So, we have the session at 5:30 p.m. We have the session at 7 p.m. and we are having the session at 4 p.m. So, let's get along with the colligative property and there we talk about something called the osmotic pressure. When we talk about the osmotic pressure, the first thing that we need to understand is something about osmosis. So, let's talk about something called osmosis. When we were doing the chapter called gaseous state, at that time we talked about something called Graham's law of diffusion. Yesterday only we had something about Graham's law of diffusion. There I told you what is the meaning of the word diffusion. Diffusion is the movement of particles from a region of their higher concentration, net movement of particles from a region of their higher concentration to the region of their lower concentration. Actually, diffusion is a two-way process, but the net movement is from the higher concentration or higher partial pressure to the lower concentration or the lower partial pressure. That is what we have as the word diffusion. Now, when we talk about osmosis, let us say we have a solution, we have a container and this container is partitioned. Here, this side we have a solution. This is a solution. And this part is the pure solvent. So, we have the solution and we have the pure solvent. Now, there is a very specific thing here, this part. This part is called semi-permeable membrane. Clear? This semi-permeable has a very peculiar property. It has a property that it only allows the volatile component to pass through it. Remember, the semi-permeable membrane allows only the volatile component to pass through it. Is this clear? Prerna, hold on, we are going to talk about. Now, when we talk about the colligative properties, we talked about the first condition and that first condition was that solute is non-volatile. Only the solvent is the volatile component. So, have you heard of it? What did I say? Hear it once again. The semi-permeable membrane allows only the volatile component to pass through. It does not allow the non-volatile component to pass through. Clear? And in this system, solvent is the volatile component while solute is the non-volatile component. So what does it mean? Semi-permeable membrane allows only the solvent to pass through. Okay, the semi-permeable membrane allows only the solvent to pass through. It does not allow the solute to pass through. Clear? Now this becomes diffusion, but diffusion with a restriction that only one component is capable of moving through. Here we have high concentration of solvent. This is pure solvent. And as the concentration of the solute increases, the concentration of the solvent decreases. Again, you need to understand that we are not going to talk about the solute because solute is not moving. So we are only bothered about the relative concentration of the solvent. The concentrated solution has a lower concentration of the solvent, whereas the dilute solution has the higher concentration of the solvent. That is what we say, dilute and concentrated is with respect to the solute and not the solvent. So, everybody has liked here? Clear? So that is what we have as the concentration of the solute and the solvent. Where we talk about the solute, where we talk about the solvent. So this is low concentration of solvent. Clear? Now the solvent particles are going to move in both the directions. They are going to move from the solution to the solvent, and they are going to move from the solvent to the solute. Both directions it's going to move. But what we find is that the pure solvent has a higher concentration while the solution has a lower concentration. The movement of the solvent particles is taking place in both the direction. It is going to take place in both the direction, but it will be more from the solvent side to the solute rather than solute side to the solvent, solution side to the solvent. So the net movement is from the pure solvent to the solution side. And if we have both the sides the solutions, then in that case it's going to be from a dilute solution, that is a lower concentrated solution, that is a higher concentration of the solvent, to the higher concentration or lower concentration of the solvent or the concentrated solution. Is this clear? Am I clear about the movement? So that is what we have as the solution. Is it clear, Prerna? Are you clear about what is the direction of osmosis? So this movement, the net movement of the solvent particles from a region of their higher concentration, that is a dilute solution, to the region of their lower concentration, that is a concentrated solution, through a semi-permeable membrane is called osmosis. Is it clear? So this is what we know as the word osmosis. So when we talk about the osmosis, osmosis is again the spontaneous flow. It is the passive flow of the solvent particles from the solvent side to the solution side, that is the dilute solution, that is the higher concentration of the solvent, to the lower concentration of the solvent or the concentrated solution through a semi-permeable membrane. So that is what we have as osmosis. So this is the net flow. Clear? Now when we are having this particular flow, then in that case this flow can actually be stopped. It can be forced to move the same amount of solvent in both the direction. Now how do we stop this particular flow? How do we stop this particular flow? We can apply a pressure on the side of the solution. Clear? Here we have the container. Here we have the semi-permeable membrane. here we have the solution, clear, and the other side we have the solvent, and now what we do is we put a piston over here and apply some pressure. We put a piston over here and apply some pressure, and when we apply some pressure, then in that case the solution side, the particles are going to move from the solution side to the solvent side, and when the particles are moving from the solution side to the solvent side, this pressure that we apply, which prevents osmosis from taking place, the pressure that must be applied on the solution side to prevent osmosis from taking place is termed as osmotic pressure. Fine. So this pressure is what we call as osmotic pressure. Quite obviously, this osmotic pressure is going to depend on the concentration. More is the concentration, more is the pressure that we have to apply on the solution side to prevent the osmosis from taking place. So osmotic pressure quite obviously is going to depend on the concentration. So osmotic pressure is represented by pi. This is the symbol which we use for the osmotic pressure. Now this pi is going to be dependent on concentration, and here the concentration is taken as molarity. Okay, or you can say amount per unit volume. It's not a necessity that we have to have molarity. We can simply have N by V, amount per unit volume, and this is also proportional to temperature. Okay, so what we find is that this pi actually equal to N by V RT. Now if N is moles and V is in liters or decimeter cube, then in that case it is going to become molarity. So pi is equal to CRT, or the concentration RT. Now this is very similar to the ideal gas equation, because here again we are going to talk about the vapors. Clear? So this is what we call as osmotic pressure. Now sometimes students might ask me, and they generally ask, so what happens if the pressure that is applied is greater than the osmotic pressure? If it is less than the osmotic pressure, then the solvent is going to move from the solvent side to the solution side. Now if it becomes more than the osmotic pressure, can we make the solvent move from the solution side to the solvent side? And then in that case it will be reverse of the normal osmosis, and this phenomenon actually takes place, and this phenomenon is termed as reverse osmosis. This phenomenon is termed as reverse osmosis when the pressure applied on the solution side is greater than the osmotic pressure. Is this clear? So anybody who has not liked the session as yet, quickly like the session. So this is what we call as the reverse osmosis, and this is what we have as osmotic pressure. Clear? So here we have the solution, the solvent, and the pressure that we apply. Here comes the semi-permeable membrane. The semi-permeable membrane is a membrane which allows only the more volatile component to pass through. Fine. So solvent actually qualifies to be the more volatile component. Fine. There are so many examples of osmosis in our daily life. We talk about the pickles, we talk about jams, jellies, we talk about so many things. Okay. So here comes osmotic pressure. Osmotic pressure is the pressure that must be applied to the solution side to just stop the process of osmosis. Clear? So here we apply the osmotic pressure. The osmotic pressure has been found to depend on concentration of the solution and the temperature. It depends on concentration, which could be molarity. It's not necessarily molarity itself. And temperature in Kelvin, so constant pi is equal to CRT, concentration into the gas constant into the temperature. So could we have the answer to this question? Calculate osmotic pressure of 0.1 molar aqueous solution of urea at 300 Kelvin. 0.1 molar. The answer is to be given in atmosphere. Now, if the answer is to be given in atmosphere, then in that case, the R value is going to be 0.0821 and temperature turns out to be how much? 300 Kelvin. So, what would be the pressure that we are expecting here? Answer quickly. Give me the answer here. I think the answer would be 2.5 atmosphere. Isn't it? Check it out. Yes. Once we have talked about the osmotic pressure, now we get along with something called abnormal colligative properties. Abnormal colligative properties. Now, whenever we talk about the abnormal colligative properties, I have my own specific example. Very, very specific example to understand abnormal colligative properties. So, let us see. There is an example. So, there is a party. Could be a marriage party, or let's say this is a banquet. Banquet hall होते हैं ना उसमें. Now, when we talk about a banquet, in that case, the invitees are not counted by the person standing at the door. The person standing at the door is not counting the invitees that this person has entered 1, 2, 3, 4. No, nobody is counting the people. What the banquet hall person counts is the number of plates which are being used. Clear? So, ideal. What is the ideal? Number of plates used is equal to number of invitees. That is how many people have been invited to the system and how many people have joined in. That is what we call as the number of plates used. This is what we have as ideal situation. Okay. So, amount of food used. Okay. And then we have the food used per person. Food used per person. Now, food used per person is equal to amount of food divided by number of plates. Is it clear? So, this is how we calculate it. Any confusion to this particular example? Now, if we relate it to the colligative properties, number of invitees is number of solute particles. Okay, the number of plates is the number of solute particles. The amount of food used is the observed colligative property. Okay, the food used per person is the molar mass. Is this clear? Anything, koi confusion, any part you would like to understand here? Now, ideally, the number of plates used should be equal to the number of invitees, and so we get the amount of food which has been used, that is measurable. How much food has been consumed, that is measurable, and we divide the total amount of food which has been used by the number of plates, and we are going to get the amount of food consumed per person. So that is going to be the case. But what can happen? Now, this is an ideality. The actuality could be a bit different from this. Now, what could be the actuality? Let us say in this banquet hall, a person is not understanding that this is by plates. So, what he does is, he picks up a plate, he has some food in it, he puts the plate back, takes another plate and has food in it, something else, and then puts the plate back, and he uses multiple plates. If he uses multiple plates, then the number of plates consumed will be more than the number of people in the banquet hall. And if so happens, now please understand, the food consumed will remain the same. One person cannot consume the food of 3 people, he is going to consume the food of 1 person only, but he has used 3 plates. So, for the same amount of food that has been consumed, the counting has increased. So, although the invitees are the same, the number of plates consumed are more, the amount of food consumed is the same, but the food counting per person would be decreased. Clear? And how does that happen? This happens if we have a solute like sodium chloride. We put sodium chloride in water. When we put sodium chloride in water, then in that case, sodium chloride dissociates to form sodium ions, and it forms the chloride ions. So, we get the sodium ions, we get the chloride ions, and each sodium chloride is going to dissociate to give us 2 particles, sodium ion and the chloride ion. So, for each invitee, we are going to consume 2 plates, and what we eat in that plate does not make a difference. Whether it is having a positive charge, whether it is having a negative charge, whether it is neutral, that does not make a difference. These are 2 particles, the 2 plates are consumed. Now, the colligative property that I am going to observe is going to be double of what it should be. The number of plates consumed are, the particles are more than what it should be. Clear? And now, if I divide it, I will get a lesser amount of food. Clear? The food consumed is the same, but the number of plates are higher. Clear? And the number of plates becomes number of plates used, number of solute particles, and which is the same as the observed colligative property. So, now the amount of food per person is going to be reduced. Clear? And so, what we get is the observed molar mass will come out to be less than what it should be. Here, since we are not bothered about the charge, we can simply put NaCl as A2, which dissociates to give 2A. We could have something like An, which dissociates to give N of A. Okay. And then we could have many other numbers also. Here we are talking about this particular thing, ANNA. So, what we know is that how many effective particles are there, what is the ratio of the actual colligative property, observed colligative property to the theoretical colligative property. That is given by a factor which is called the Van't Hoff factor. Clear? Fine. Now, this was the case of dissociation. That is, the substance that we have added dissociates to give more amount of particles. So, this is the case of dissociation. But then we can have a case of association as well. It is possible that a person picks up the plate and then another person says, yeah, I don't want to have the another plate, I'll have some food from your plate itself. Now, quite obviously, if another person is having the food from the same plate, then the amount of food which is consumed becomes more. When the amount of food which is consumed becomes more, then in that case, the plates are consumed the same number, but the food consumed is more. So, the food consumed per person will come out to be more than what is expected. And now we are going to get a higher molar mass. Now, this is what we call as association. Like something like we have acetic acid CH3COOH. Now, instead of water, if we take acetic acid and benzene, then acetic acid has a tendency to dimerize. That is, two acetic acid molecules are going to get CH3COOH whole twice. Or you can just not put it 2 here, you can even put it as CH3COOH in benzene gets converted into 1/2 CH3COOH whole twice. In this case, it becomes A gets converted to 1/n, AN. See, here is 2, here is 2. So, here is N, here is N. N is the number of particles which are joining together to form a single particle. Is that clear? Now, we are going to observe a higher molar mass. Now, this is the case of association. This is the case of association. Clear? So, that is what we have as association. Now, we have a factor called I. Now, this I is called Van't Hoff factor. This I is called the Van't Hoff factor. When you talk about the Van't Hoff factor is the observed colligative property divided by expected colligative property. That is what we have as the observed concentration divided by expected concentration. That is equal to the actual molar mass by observed molar mass. So, this is what we have as the Van't Hoff factor. Now, for dissociation, Van't-Hoff factor is greater than 1. For association, Van't-Hoff factor is less than 1. Is this clear? So this is what we have something as the Van't-Hoff factor. Now it is not a necessity that the substance completely dissociates or associates. Like we have some compound AN. Now it is an equilibrium with Na. Now we are talking about dissociation. Now let's say it is 1 minus D, dissociation, or you want to get, say 1 minus alpha, 1 minus P, 1 minus whatever you want, that does not make any much of the difference. And here is going to be ND. The number of particles is going to be 1 minus D plus ND, and that's equal to the Van't-Hoff factor. And this is the relation of the Van't-Hoff factor with the degree of dissociation. So D is degree of dissociation. Clear? On the other hand, if it is A getting converted to 1 by N AN, then it is 1 minus A, where A is the degree of association. Here it is going to become A by N, and Van't-Hoff factor would become 1 minus A plus A by N, where A is degree of association. Have you copied it down? All the students who have joined the session, have they liked the session? And remember, at 5:30 p.m. we have a special class of chemistry where we are going to do the concentration units, and we are going to talk about the questions of concentration unit. We are going to have quiz, we are going to have the solutions, we are going to have the answers. So please join at 5:30 in the special class. For that, you need to download the Unacademy app, and while downloading and joining with the Unacademy app, you can simply put in the code AVLIVE, AVLIVE, and join with me. Okay, clear? So that's what we have as degree of dissociation and degree of association, and that's what we have as the Van't-Hoff factor. So abnormal colligative properties: if the solute associated or dissociated in the solution, then experimental observed actual value of colligative property will be different from theoretically predicted value. When we talk about the electrolyte solutions, they dissociate, the number of particles turns out to be greater than the actual particles, and something like here. So here we are going to get more particles. So the colligative property observed is going to be higher than expected, and this can be calculated in terms of Van't-Hoff factor, and this is what we have as observed colligative property upon calculated colligative property, theoretical molar mass upon experimental molar mass. Is that clear? So let's have the question: when 20 grams of naphthoic acid is dissolved in 50 grams of benzene, Kf is given to you. Okay, now we can have the relation of the colligative properties. So we know that Van't-Hoff factor is equal to the observed colligative property upon theoretical colligative property. So that would mean observed colligative property is equal to Van't-Hoff factor multiplied by theoretical colligative property. Okay, it is observed colligative property upon theoretical colligative property. So that would mean, let us see, we talk about the different colligative property. One is the relative lowering in vapor pressure. When we talk about the relative lowering in vapor pressure, that is going to be delta P upon P naught. the expected or the theoretical colligative property is actual mole fraction of the solute. That is mole fraction of the solute. So, to use the Van 't Hoff factor, we simply multiply it by the Van 't Hoff factor. This is the relative lowering in vapor pressure and its relation with the Van 't Hoff factor and the actual value. That is the first one. The second one is what we call as the lowering in the elevation in boiling point. Elevation in boiling point is delta TB. Now, that's initially when we talk about the ideal, it's KBM, but now it needs to be multiplied by the Van 't Hoff factor, Van 't Hoff factor multiplied by KBM. In the same manner, we have the depression in the freezing point. This again turns out to be the Van 't Hoff factor multiplied by KFM. KFM is the ideal value and Van 't Hoff factor is there to relate the ideal value to the observed value. Is this clear? And then we have something called the osmotic pressure. Osmotic pressure pi, that is equal to concentration RT. You need to multiply again with the Van 't Hoff factor to get it. It is equal to ICRT. This is what we need to understand. Anything you would like to ask here? Prerna, when I am solving all your questions, then why do we need the Google Meet? And if you want to really have the session of the Google Meet, why don't you join with me at 5:30 p.m. That session is as good as Google Meet, and in fact, it's better. Prerna, at 5:30 p.m. join with the Unacademy app. That is better than Google Meet. Is this clear? So let's have this particular question. When 20 grams of naphthoic acid is dissolved in 50 grams of benzene, a freezing point depression of 2 Kelvin is observed. The Van 't Hoff factor I is freezing point depression. So we have the formula delta TF is equal to Van 't Hoff factor KFM. Okay. So delta TF is given as 2. Van 't Hoff factor I don't know. KF is equal to 1.72. 20 gram of naphthoic acid. So it is going to be molality is going to be 20 divided by the molar mass of naphthoic acid into the 50 grams of benzene. To make it in kilogram, that is 1000 divided by 50. Could we just get the molar mass? C11H8O2. More is the freezing point, lower is the Van 't Hoff factor. More is the boiling point, more is the Van 't Hoff factor. Lower is the freezing point, more is the Van 't Hoff factor. Okay. Delta TF, more is the value of delta TF, lower would be the freezing point and higher would be the value of Van 't Hoff factor. Is it clear? Okay, so these are the various concentration units. You can simply take a screenshot. I'll just go out of the frame. You can just take a screenshot of this, the mind map. And then we have the Raoult's law, the positive deviation, negative deviation, and the various values. So we are having 3 p.m. biology with SACHIN KAPUR sir, 4 p.m. chemistry with me. Join with us on the Unacademy app, download the Unacademy app, select your goal and join with the code using AV Live. So join with the code AV Live, NEET UG subscription, NEET UG subscription is there. You can go along with the subscription also. Unacademy.com/Anoop Vashishtha is my page on Unacademy where you can join with me and follow me. Clear? So you can just follow me there, join with me and attend all the sessions, because here on this page you are going to get all the information about all the classes, whether it be the plus courses, whether it be special classes, you will get all the information here. Yes, Shubham, you are going to get the PDF on the Telegram channel. Subscribe to the Unacademy NEET Elixir for the best live classes. Like, share and subscribe, and also comment. So we are going to meet with you at 5:30 p.m. in the special class. So just go ahead and join the special class today itself. Okay? Take care. 5:30 p.m. in the special classes. Bye-bye.